All right, welcome to the first example of section 6.6. In this one, we're going to be solving equations that have our variables in the exponents. So if you look at this first one, we are solving for x, but you'll notice that first of all, we've got variables on both sides of the equation. So 100 to the x power, and then equals 1 over 10 to the x minus 3 power. So we've got an equation here with variables on both sides, and the variables are in our exponents. So what we're going to do is we're going to use all the rules and properties of logarithms that we've learned so far this chapter to simplify this equation and solve for our variable. Before we can get into this, if you look in the journal, this is on page 181, we have some properties of equality for exponential equations. So what this first property states is if b is a positive real number other than 1, then b to the x power equals b to the y power if and only if x equals y. Basically what that means is that if you have an equation with two bases with exponents on either side, that if the bases are equal, then whatever their exponents are must be equal as well. So, for example, if you have 3 to the x power equals 3 to the fifth, then you can just set the exponents equal to each other, x and 5. So you get x equals 5, which makes sense because 3 to the fifth power obviously equals 3 to the fifth power, so x must equal 5. What this means is that in order to solve equations that have bases with exponents, you can use this property if you're able to make the bases equal to each other on either side. So sometimes that means rewriting or rearranging one side of your equation to make the bases equal. Let's look at this first example right here. So we have 100 to the x power equals 1 over 10 to the x minus 3. So right now, our bases are not equal to each other. We've got 100 on the left side and 1 over 10 on the other. So what we want to do in order to use this property, we need to see if we can maybe rewrite these bases so that they are equal to each other. Now, right away we can tell that these are both powers of 10. For example, 100 is just equal to 10 squared. And if we look at 1 over 10, that's also a power of 10. That is just 10 to the negative first power. So right here, our equation, even though at first glance it doesn't look like we have the same base or that we can just set the exponents equal to each other, by actually taking the current bases of 100 and 1 over 10 and rewriting them as powers of base 10, we can actually do this. So again, let's remember 100 is just equal to 10 squared, and 1/10 is equal to 10 to the negative first power. So if we go ahead and replace 100 with 10 squared and 1 over 10 with 10 to the negative first power, now we've set both sides equal to the same base. Now let's go ahead and use to simplify this and get rid of the parentheses. We know 10 squared to the x power is just 10 to the 2x, and 10 to the negative first power to the negative, or to the x minus 3 is just 10 to the negative x plus 3. So you can see from this step right here, all we did is distribute our exponents, and now we have an equation with base 10 on both sides. So here 10 to the 2x is equal to 10 to the negative x plus 3. Based on our property of equality for exponents right here, we know that this equation must be true if and only if the exponents are equal to each other. So now we can just forget about the bases. We can just write our exponents as a single equation. So we can write 2x equals negative x plus 3. Now this gets rid, first of all, our variables are out of our exponents now, and we have just a simple algebraic equation that we can just rearrange, isolate our variable, and solve. So if we take this, we go ahead and just add x to both sides, divide by 3, and we get x equals 1. Now, if you go back and check, you'll see that this does make sense. If we plug 1 in, we get 100 to the first power, which is just 100. And then we get 1 over 10. For an exponent of 1 minus 2, we get 1/10 to the negative second power, which is also 100. So that works out for us. Now, on this second problem right here, we've got 2 to the x power equals 7. So on this one, if we look back and we've got another property, instead of our properties with exponential equations, we're going to look at our property for logarithmic equations. So what this property says is that if we have the log base b of x equals the log base b of y, this statement is only true if and only if x is equal to y. What that means is that just like with our exponents, if we have the same base, then our exponents must be equal. If we're taking the logs on both sides and the base is the same, then whatever we're taking the log of must be equal to each other. So for example, if we had log base 2 of x equals log base 2 of 7, we know that x must equal 7 for this to be true. So let's go back and look at our problem here. So we have 2 to the x equals 7. So if we go ahead and let's take that. Now, it's not quite as clear. We don't have a log in this equation yet. We don't have exponents on both sides. For example, 7 is not a power of 2, so we can't rewrite this and set the exponents equal to each other. But one thing that we can do is if we take the log of both sides, in this case the log base 2, what that's going to allow us to do is actually get rid of, or get our variable out of our exponent on the left-hand side. So again, in this second step, we're taking the log base 2 of both sides. So the log base 2 of 2 to the x power equals log base 2 of 7. So the reason we did this is if you look here and remember our inverse property, if we take the log base 2 of 2 to the x power, the log base 2 and the 2 just cancel out, and we're left with x equals a log base 2 of 7. So again, what we've done right here is we've taken a problem and we took the log of both sides because taking the log is going to allow us to bring our variable out of the exponent and isolate it. Now we can just use our calculator for log base 2 of 7, or you can use the change of base property and you end up with x is roughly equal to 2.807. You always want to round to 3 decimal places on this when you're giving a answer that has a long repeating decimal. All right, so the problems I want you to try right now are right here, A and B. So you've got 2 similar types of problems. I want you to solve each of these, and your final answer, you're solving for x, so you should have a value for x on each of these. And when you write them in, go ahead and indicate what your answer for A is and your answer for B. So you should have both answers in the same answer box here.